This is question number 11. Okay. Particle A of mass 0.26 kg and particle B of mass 0.52 kg are attached to ends of light inextensible string. So let's consider this figure. Okay, so this particle B will have a downward force, which would be the weight of this particle. Weight is mass times gravitational acceleration. So 0.52 times 10, which is going to be 5.2 newtons. Okay. For A, the weight would be vertically downwards, but we will be resolving it in the components. This component would be mg cos theta. So m is 0.25. So mg would be 2.6. Cos, the angle is alpha. And similarly, this downwards force is mg sine theta. So that's going to be 2.6 sine alpha. Okay. With respect to A, tension will be outwards. With respect to B, tension will be upwards since tension always points away from the object. Okay. Next, it says that the string passes over a small smooth pulley P, which is fixed at the top of the smooth plane. The plane is inclined at an angle alpha to the horizontal. Sine alpha is given and cos alpha is given. So we have the values of this cos alpha and sine alpha as well. Okay. A is held at rest at a point 2.5 meters from P. Okay, and we can see that in figure and with part AP of the string parallel to the line of the greatest slope of the plane. B hangs freely below P at a point 0.6 meters above the floor. A is released and the particle starts to move. Okay. If the particle moves, there will be acceleration in the system. Find the magnitude and acceleration of the particles and the tension in the string. So now we'll be applying Newton's second law in on particle B as well as particle A. Okay, they have not mentioned friction in this question. That means there's no friction, which makes this question simpler. So this particle would move in this direction and B would move downwards. So we're going to apply Newton's second law on this, which is forward force minus backward force is equals to ma. At particle A, the forward force is T, the one in the direction of motion. The backward force is the component of weight, 2.6 times sine alpha. We know sine alpha is 16 over 65 is equals to ma. Mass is 0.26 and A is the acceleration. Okay. And then at B, the forward force is the force in direction of motion, which is 5.2, the weight. The backward force is tension, is equals to ma. Again, mass here is 0.52 and acceleration is A. Now we have two sets of simultaneous equations. You will solve these and get the value of A and T. I'm just directly writing the answers. A will come out to be 5.85 meters per second square, and T will come out to be 2.16 Newton. Okay. In part 2, it says find the speed with which P reaches the floor. Okay. With which B reaches the floor. Okay, let's take a look at B. So currently at this point, its U is 0. Initial speed is 0. We know that as it moves, it covers a distance of 0.6 meters. So S is 0.6. And we know the acceleration of both the particles. That is 5.85. And we need the value of V. So we're going to use V square equals U square plus 2AS. And then we'll take square root to find V. So V square equals U square, which is 0 square, plus 2 times A times S. This would come out to be 2.6486, which rounds to 2.65 meters per second, in 3 significant figures. Okay. and the distance of A from P when A comes to instantaneous rest. Okay, so now as B falls to the ground, A will move upwards. Oops. Okay, never mind. All right, so as B falls to the ground, B covers a distance of 0.6 meters. So A will also cover a distance of 0.6 meters in this direction. That's the new position of A. And this distance would be 1.9. We do 2.5 minus 0.6. So this would be 1.9 meters. Okay. Now what happens is that since B hits the ground, right after that, the string slacks. The string will slack and this A will continue moving upwards till a certain point when its speed, the final speed becomes zero. So the string slacks, but A continues to move upwards for a while till it reaches a point where the speed becomes zero. Now we need to find what distance would this be between the final position of A and B. So for that, what we need to actually find is this distance and then subtract it from 1.9 to get the green distance. Okay. Now, how do we find the blue distance? What is the speed of A at this position? That is the same as speed of B right before it hits the ground. That was this 2.6486. So we're going to write U is equals to 2.6486. That becomes U for this part of the journey, the blue journey. Okay, so for the blue journey, we know U is 2.6486. We know V is 0. We now need the acceleration of this blue part of the journey because the acceleration will now change. Why will it change? Because the string has slacked and now the tension in the string is 0. So now the forward force becomes 0. So we're going to reuse this formula, but now the forward force would be 0. So let's reapply it. Forward force at A again. Forward force is now 0 because the string has slacked, minus backward force, which is the gravitational component, which will stay the same, is equals to mass times acceleration. A will come out to be some negative value, which would be minus 2.461, or it's minus 32 over 13. It's better to use the exact value. Okay. Now we have the acceleration as well, or the deceleration, minus 32 over 13. And we need S, and then we subtract the S from 1.9. Okay, S would be found by using V square equals U square plus 2AS. So 0 square is equals to 2.6486 whole square plus 2 times A times S. Solve this. It comes out to be 1.4264, and then we do 1.9 minus answer, which gives 0.47355, rounded to three significant figures, 0.474 meters. This should be the final answer.